We are now going to start the third module of chapter 3, where we will talk about invertibility of linear transformations. We will learn a special name, they are called isomorphisms of vector spaces, and we will see how to determine when a linear transformation is an isomorphism. Let V and W be vector spaces over a field F. A linear transformation T from V to W is said to be an isomorphism if there exists a linear transformation U from W to V, that is in the other direction, such that T composition U is the identity operator on W and U composition T is the identity operator on V. The linear map U is said to be an inverse of the linear map T, and vector spaces V and W are said to be isomorphic if there exists an isomorphism T from V to W. A map is called invertible when it has an inverse, and it is easy to prove that inverse of a map T, if it exists, then it is unique, and that is called the inverse of T, and we usually denote it by T inverse. So, in the case of an isomorphism, inverse of a linear map, which is also a linear map, that is what we call T inverse. In this case, U is T inverse. Now, what is more interesting about a linear map is that inverse of an invertible linear map is always linear. So, if there is a linear map T from V to W, and if we know that the inverse map of T exists, then we can prove that the inverse map is also a linear map from W to V. This theorem lists down some simple properties of an isomorphism. Suppose that T from V to W is an isomorphism with the inverse U, then T is 1 1 and onto, T circle U inverse is U inverse circle T inverse, and the inverse of T inverse is T. In particular, T inverse is invertible. So, proof of statement 1 is true because T has an inverse if and only if it is 1 to 1 and onto, and 2 and 3 follow easily from the fact that an inverse, if it exists, then it is unique. So, all we have to do is that we consider this candidate U inverse circle T inverse and then composite with T circle U and show that that is the identity operator. And similarly, for the third statement, we consider T inverse composite with T and show that it is the identity operator in both the directions, and that proves this theorem. Another theorem which says that if V and W are finite dimensional vector spaces of equal dimension, a linear transformation T from V to W is an isomorphism if and only if rank of T is equal to dimension of V. This is true because T is an isomorphism if and only if T is onto, if and only if rank of T is equal to dimension of V. Well, we have already seen that if V and W are finite dimensional vector spaces of equal dimension, then T from V to W is 1 to 1 if and only if T is onto. Therefore, it is enough to have onto property for T in order to have isomorphism between V to W, and onto-ness is equivalent to range of T is equal to W. In other words, rank of T is equal to dimension of V. So, it is because of rank nullity theorem. Let us revisit those operators, the rotation operator T theta on R2 and the reflection operator Txy equal to x comma minus y on R2, and both are onto maps, onto linear maps and hence isomorphisms, whereas the projection operator Txy equal to x comma 0, that is projecting onto the x axis, this projection operator on R2 is not onto and therefore it is not an isomorphism. Now we prove this lemma which says that if T from V to W is an isomorphism and if V is finite dimensional, then W is also finite dimensional and conversely, and in this case, that is when there is an isomorphism from V to W and when V is finite dimensional, then dimension of V is equal to dimension of W. Let us prove this. Let us start with a basis V1, V2, Vn for the vector space V. We have seen before that Tv1, Tv2 and so on Tvn, this set spans the range of T which is W. Why? Because T is an isomorphism, therefore it is onto and therefore range of T is W. We therefore have a finite spanning set for the vector space W and therefore it is finite dimensional. Conversely, if we want to show that W is finite dimensional implies V is finite dimensional, all we have to do is that we just work with the inverse map T inverse which is from W to V and proceed along the same line. Now we prove that dimension of V and dimension of W must match. So suppose that V and W are both finite dimensional with an isomorphism T from V to W. T is an isomorphism, therefore it is 1 to 1 and therefore the kernel of T is trivial, which means that nullity of T must be 0. And therefore by the rank nullity theorem we know that rank of T must be equal to dimension of V. So that proves our statement, because dimension of V which is rank of T, but rank of T is nothing but the dimension of image of T and image of T is W, therefore it is dimension of W. Now a very important theorem. So let us start with a finite dimensional vector space V over a field F with an ordered basis V1 to Vn. Let us fix n elements W1 to Wn in W. Then the statement is that there exists one and only one linear transformation T from V to W which takes Vi to Wi for all I equal to 1 to n. So let us understand the statement very well before we start proving it. It says that if we have a finite dimensional vector space with a basis V1 to Vn, then if we assign the values W1 to Wn to V1 to Vn through a map T, then there is only one such linear transformation T which assigns the values Wi to the vectors Vi's. Proof: let x be a vector in V, then x can be written as a linear combination of the basis vectors Vi. So x is equal to summation I equal to 1 to n ai Vi for unique choice of scalars a1 to an. That is because V1 to Vn is a basis for V. We define T of x is equal to summation I equal to 1 to n ai Tvi, and Tvi is Wi, so it is summation I equal to 1 to n ai Wi. First of all, we observe that T is a well defined function because of the uniqueness of the scalars ai. That means that x can be written in that linear combination of vi's in only one way, and therefore this definition is well defined, and it is very easy to check that T is a linear map, that is T is additive and homogeneous. So, we do have a linear map T from V to W such that T of Vi is equal to Wi. Why is that so? Because for Vi the scalars ai are nothing but ai would be 1 and all other scalars would be 0, and therefore T of Vi would be exactly equal to Wi because of the way we define T. Now we have to show that T is the only such linear transformation with this property, that is T of Vi is equal to Wi. So, suppose that U is another linear map with this property U of Vi is equal to Wi, then U of x will also be is equal to T of x, and that is because of the linearity of U. We therefore have Ux is equal to Tx for all x in V, and therefore U is equal to T, showing that T is unique. Now this corollary, which is essentially a restatement of the theorem you have seen just now. So let V be a finite dimensional vector space with an ordered basis V1 to Vn. Let T and U be linear transformations from V to W with the property TVi is equal to UVi for all I equal to 1 to n. Then U is equal to T. Well, this is what we have proved, and what it says is that if two linear maps agree on a basis of a vector space, then they must be the same. We will use this important fact to prove some theorems on the invertibility of a linear map. What we have seen just now is something very interesting about linear maps. If we have a vector space V with an ordered basis, and if we want to define a linear map from V to W, then it is enough to assign values to the basis vectors and then extend it linearly. Well, this takes care of the well-definedness of the map, especially because in a vector space every vector is uniquely expressed in terms of the basis vectors. We now talk about the matrix representation of the inverse linear map with respect to ordered basis. The theorem says, let V and W be finite dimensional vector spaces over a field F with ordered basis B1 and B2 respectively. Let T from V to W be a linear transformation. Then T is an isomorphism if and only if the matrix box T B1 B2 is an invertible matrix. And moreover, the matrix of the inverse map T inverse with respect to B2 B1 is nothing but the inverse of the matrix T B1 B2. How to prove this statement? So suppose that T is an isomorphism, then we know that dimension of V must be equal to dimension of W, let us say n. Therefore, the matrix T B1 B2 is an n cross n matrix. Now consider the identity operator IV with respect to the ordered basis B1. Then the matrix representation of IV with respect to B1 would be IN, the identity matrix, N cross N identity matrix in fact, and that is equal to the matrix of T inverse composition T, because IV is T inverse composition T, and that is with respect to the ordered basis B1. And we know that the matrix of the composition map is given by the product of the matrices T inverse with respect to B2 B1 and then T with respect to B1 B2. Therefore, we have proved that the product of these two matrices, the matrix of T inverse and the matrix of T with respect to the basis B1 B2, then this is IN. And a similar argument where we just have to flip the sides of T and T inverse, and then we can show that the matrix T with respect to B1 B2 times the matrix T inverse with respect to B2 B1 is also equal to the N cross N identity matrix. This proves therefore that the matrix T B1 B2 is invertible, and the matrix of T inverse with respect to B2 B1 is nothing but the inverse of the matrix T B1 B2. Let us now prove the converse. So, we start with the matrix T B1 B2 and call it A, which is an invertible matrix, and we are trying to show that the linear map T is an isomorphism. A is invertible as a matrix, therefore, there is an N cross N matrix B such that AB is equal to BA is equal to IN, that is the N cross N identity matrix. Now, suppose that B1 is V1 V2 Vn and B2 is W1 W2 Wn are the ordered basis for V and W respectively. Now, we define the map U from W to V as U of Wj is equal to summation Bij Vi, the summation is over I equal to 1 to n, and this is true for every j equal to 1 to n. And it is clear from the definition that the matrix representation of U with respect to the ordered basis B2 B1 is nothing but B. And therefore, the matrix of U circle T is the matrix of U product matrix of T, and that is equal to B times A, which is equal to the N cross N identity matrix. But the N cross N identity matrix is nothing but the matrix representation of the identity operator IV with respect to the ordered basis B1. This therefore shows that U circle T has to be the identity operator. Why? Because both the operators agree on the basis B1 of V. So, by the theorem we proved, it shows that the operators U circle T and IV have to be the same. And similarly, if we just reverse the directions of U and T, then we can prove that T circle U is the identity operator of W, and therefore we have proved that U is equal to T inverse. So, T is an isomorphism. Let us revisit the example of the rotation operator T theta from R2 to R2 given by T theta of xy is equal to x cosine theta minus y sin theta comma x sin theta plus y cosine theta. And with respect to the standard basis B of R2, its matrix representation is cosine theta minus sin theta in the first row and then sin theta cosine theta in the second row, and we have already seen that this matrix is an invertible matrix with the inverse cosine theta sin theta in the first row and minus sin theta cosine theta in the second row. Now we list down some results which are easy consequences of the theorems we have proved just now. It says that if V and W are finite dimensional vector spaces, and if dimension of V is n and dimension of W is m, with ordered bases B1 and B2 for V and W respectively, then 1. V is isomorphic to W if and only if dimension of V is equal to dimension of W. 2. V is isomorphic to f to the power n, that is the vector space over the field f, that is the Cartesian product of f n times, and that is true if and only if dimension of V is n. Now consider the function phi from LVW, that is the collection of all linear transformations from V to W, which is also a vector space over the field f, to MMNF, that is the collection of all m cross n matrices with entries from F, and the map is given by phi of t is equal to the matrix representation of t with respect to the basis B1, B2, and the fact is that this map phi is an isomorphism. The function phi B1 from V to f to the power n given by phi B1 of x is equal to box x B1, that is the coordinate vector of the vector x with respect to the ordered basis B1, and this function is an isomorphism. Proving these statements essentially use the theorems we have proved, and you can see that statement 2 follows from statement 1, because if we take W to be f to the power n, then dimension of W is dimension of f to the power n, and we know that that is n because E1, E2, En is the standard basis, and the other statements can be verified easily. We now introduce the concept of basis change matrix. So let us start with this example. Let V denote the vector space R2, and we consider these two ordered bases, B1 which is the standard basis for R2, that is 1 0 0 1, the standard basis vectors, and B2 is another ordered basis where the vectors are 1 0 and 1 1. Let us look at the identity operator IR2, that is from R2 to R2, and if we follow the definitions, then we can see that the matrix representation of IR2 with respect to the basis B1, that is the standard basis, is nothing but the 2 cross 2 identity matrix, whereas the matrix representation of IR2 with respect to the basis B1 and B2 is the matrix where the first row is 1 comma minus 1 and the second row is 0 comma 1. It is a different matrix. We now prove this theorem. Let B1 and B2 be ordered bases for the finite dimensional vector space V. Let Q denote the matrix of the identity operator IV with respect to the basis B2, B1. Then this matrix Q is invertible, and given any vector V in V, we have the coordinate vector box V with respect to the choice of basis B1 is equal to Q times box V with respect to B2, which is the coordinate vector of V with respect to the basis B2. Let us see the proof of this theorem. For the first part of the statement, we can use the fact that IV, composition IV is IV, and therefore the matrix Q is invertible. And for the second part, we see that if small v is a vector in V, then the coordinate vector for V with respect to the basis B1, that is box V B1, is nothing but IV of V with respect to B1, and this can be written as IV of B2 B1 product box V B2. So, IV B2 B1 is the matrix representation of the identity operator with respect to B2 and B1, and box V with respect to B2 is the coordinate vector. Now, IV B2 B1 is Q, so this is equal to Q times box V with respect to B2. Now, this matrix Q, which is the matrix representation of the identity operator on V with respect to the basis B2 B1, is what is called the basis change matrix. And we can say by the second part of the theorem proved above that Q changes the B2 coordinates of a vector into its B1 coordinates. Therefore, the matrix Q inverse changes the B1 coordinates of a vector into its B2 coordinates. So, for this reason Q is also called the coordinate change matrix. The theorem says that if T is a linear operator on a finite dimensional vector space V over F, and if B1, B2 are ordered bases for V, then if we assume that Q, which is the matrix representation of the identity operator IV with respect to B2, B1 is the basis change matrix, then the matrix representation of T with respect to the basis B2, that is T B2, is equal to Q inverse times the matrix representation of T with respect to the basis B1, that is T B1 times Q. How to prove this? We observe that Q times T B2 is nothing but IV B2 B1 times T B2 B2, because T B2 means T B2 B2, we have already made this remark before, and by the theorem we proved that the matrix representation of the composition map is the product of the individual matrices. So, it is equal to IV composition T B2 B1, but we know that IV composition T is the same as T composition IV. So, this is equal to T composition IV B2 B1, and that is T B1 B1 times IV B2 B1, but IV B2 B1 is Q, therefore, this is T B1 times Q, and therefore, Q T B2 Q inverse is equal to T B1. This proves the theorem. Well, this is the point to give this very important definition of similarity of matrices. Suppose that A and B are two n cross n matrices over a field F. We say that A is similar to B over F if there exists an invertible matrix Q over F such that B is equal to Q inverse times A times Q. We will see that this concept would come back again, where the basis change matrix Q will be extremely important in various cases, especially when we talk about symmetric matrices. We will see in future that matrix representations of a linear transformation can take simpler form if we choose bases suitably. And when we try to write that simpler matrix representation, then the basis change matrix comes into the picture.